Hello, welcome to the next lesson in CE 3305, Engineering Fluid Mechanics. And now we're going to discuss the topic of linear momentum. Remember last time we pretty much beat to death the conservation of mass. And this is the next step in the kinematic principles that are useful. For a system, conservation of linear momentum is mass times change in velocity with time, that's mass times acceleration, of the system is equal to the sum of the forces on the system. Linear momentum is going to relate forces to the change in velocity. And we use Reynolds transport theorem again to move between the system and the volumetric description. If we apply the Reynolds transport theorem, RTT, we'll have m dv dt of the system is equal to d by dt of mass times velocity. These are our extensive properties. And so the corresponding intensive property, beta, is mass times velocity over mass. So that's the intensive property per unit mass. So mv is momentum, so that's the intensive momentum per unit mass. And per unit volume, we have it as equal to rho times velocity. Now here's where my notation matters, because now we have v as a velocity and that v is a volume. So let's apply these to the system and see what we come up with. What we have is dv dt, the system equals d by dt, integral over the control volume of beta, rho d volume, plus the integral over the control surface of beta, rho, v dot dA. In this case, that equals the sum of the forces. So for linear momentum, B is equal to mass times velocity. Beta, therefore, is velocity. So now we'll just write these terms. So rearranging sum of the forces, d by dt, integral over the control volume of rho velocity d volume, plus the integral over the control surface of rho velocity v dot dA. So this is the net forces on the material in the control volume, body plus surface. This is the rate of change of linear momentum in the control volume. And this is net momentum leaving the control volume across the control surface. The result is that the sum of the external forces is equal to the rate of change in linear momentum plus the net momentum leaving the control surface. This is a vector equation. Forces are a vector, so this may have 1, 2, or 3 components depending on your coordinate system. To apply this, we use it much like we did with continuity of mass. We'll select an inertial reference frame. It just means it's not accelerating. Indicate positive and negative coordinate directions. Draw control surface, control volume. On that, indicate forces. Don't forget the weight. Velocities. And the dA vectors. So let's illustrate this with an example. So here's the first example, and in this case I just printed a problem out. We have a water jet pump which has jet area of 0.1 meters squared and a jet speed of 30 meters a second. The jets contain a secondary stream of water with approach velocity of 3 meters a second. Total area of the duct, jet plus secondary stream, is 0.075 meters squared. Water is completely mixed, leaves the jet pump as a uniform stream. The pressures of the jet and secondary stream are the same at the pump inlet. Determine the speed of the pump and the changing pressure from location 1 to 2. So here's our jet pump, and let's just apply our methodology. So I'll pick a coordinate system here, X. I'm going to create a control volume. Now you can draw right on the drawing if you can keep track of what everything is. I'm just going to do it next to it. Control volume is the water in the pump at any time. Control surface is the bounding surface as shown. And location 1 is here, and 2 is here. Okay, next thing is we want to indicate positive coordinate directions is done. We want to indicate forces. The only force here that we have a weight force, and we would have a reaction force if we had friction. Our next is to indicate velocities and dA vectors. So here we have two areas. We have the area of the jet. We'll call that dA of the jet. And we have the outward area of the free stream, dA of S. Here we have a u sub jet and u of the free stream. And we know the numerical values. We're given that in the problem statement. At location 2, we have dA2, and we have u2. At location 1, we also have a pressure. So there's a P1, and that force is going to be pushing in that way. And at location 2, we have pressure pushing backwards, P2. So we have the pressure forces, velocity, and the vectors. And then I'll just show the boundary. Okay, so the only faces of interest are this green and this green. So our solution is to apply continuity. So 0. So when we're using momentum, we'll almost always have to apply continuity also. d by dt integral over the control volume of rho d volume plus the integral over the control surface of rho v dot dA. That will zero out because the control volume is known to be fixed in size. So all that we have left is the integral over the control surface of rho v dot dA. So this is continuity. Well, what's that equal? Well, we'll start at position 1. Equals minus rho u jet, area of the jet. Go ahead and just do the integration in our heads. Minus rho u free stream, area of the free stream. And on the right side at position 2, we have rho u2 a2. We could put numerical values in if we wanted. AJ is 0.01 meters squared. A free stream is going to be 0.065 meters squared. And A2, which has to be the sum of those two areas, is 0.075 meters squared. So we're using this principle and that, and from the drawing, and the jet's a portion of the total area. We have U jet is 30 meters per second, and we have U, the free stream, is 3 meters per second. So we have to find U2. So taking this equation, the constant density, the density can be divided out, and we make some rearrangements, and we have U2 times area 2 equals Uj area j plus U free stream area free stream. Therefore, U2 is equal to Uj area j plus U free stream area free stream divided by area 2, and we put in numbers. U2 is 30, 0.01 plus 3, 0.065 divided by 0.075 equals 6.6 meters per second. So the jet pump accelerates the free stream entering at 1 to 6, a little bit more than 6 meters per second, leaving it. Okay, so we determined that part from continuity, but what about the pressure rise? That's where we're going to have to use the momentum equation. So for momentum, we have sum of the forces equals d by dt integral over the control volume of v rho d volume plus the integral over the control surface of v rho v dot dA. So let's draw ourselves a force diagram and see what forces we have to work with. So the only forces we have are the two pressure forces plus the weight of the water in the volume. Here's my control volume again. On the left side, we have a pressure force, and we're told it's pretty much the same all the way across. There's P1. On the right side, we have P2 pushing back, and there's a weight force. Coordinate system, X and Y. Well, let's write the sum of the forces. Y direction is not going to be useful in this case. So sum of forces in the X direction is P1, A1, I minus P2, A2, I equals P1 minus P2 area times I. So if we know what the cross-sectional area is, the sum of the forces in X has to be equal to the differential pressure. Otherwise, it'll start to accelerate off the sheet of paper. Of course, it's gone now, so maybe that happened. Just kidding. d by dt, integral of the control volume, v rho d volume equals 0 because we have steady flow. Momentum in the control volume is not changing with time. Integral of the control surface of v rho v dot dA. Now we have to look at the left face and the right face. In the left face, we have the areas are pointing outward and the flow is coming in. In the right face, areas pointing outward, flow is going out. So the dot product of these will produce a negative value. The dot product of those will be a positive value. So this is equal to Uj minus rho Uj Aj, the I direction, plus U free stream minus rho U free stream, area of the free stream in the I direction. So that's the momentum of the jet entering and the momentum of the free stream entering. Plus, at the right edge, U2 with or without U, rho U2, A2 in the I direction. And now we're going to take this, add it to that, and equate it to the sum of the forces. In doing so, we have the following. P1 minus P2, area, I direction equals rho U2 squared, A2 I direction minus rho Uj squared, Aj in the I direction minus rho U free stream squared, A free stream in the I direction. Okay, so I'm going to drop the vector notation for clarity because everything's in the I direction. P1 minus P2 times area equals rho U2 squared A2 minus Uj squared Aj minus Us squared As. P1 minus P2, which is what we're after, is equal to rho over the area times U2 squared A2 minus UJ squared AJ minus U free string squared A free string. If we put numerical values in, we get change in pressure would be 1,000 kilograms per meter cubed, 0.075 meters squared, 6.6 squared times 0.075 minus 30 squared times 0.01 minus 3 squared times 0.065 is going to equal minus 84,240 pascals. So what that implies is for that to be true, P2 has got to be bigger than P1. Does that kind of make sense? Sure it does. Would you put your eyeball on the downstream side of that jet pump, or would you rather have it on the free stream upside? Well, you'd rather have it on the upstream side because that's only 3 meters a second hitting your eyes instead of 6. The main value of this example is when we look at the V dot A concept. So let's just look at just the jet. We had area of the jet, velocity of the jet. Written as a vector, area of the jet is equal to minus A sub jet I. Velocity of the jet is equal to U sub jet I. When we do V rho V dot dA, we're doing velocity U sub jet I times rho U sub jet I dot minus A sub jet I. I dot I is 1. So we come up with minus UJ squared rho AJ, and it's still the I component from this part of the vector operation. Okay, that concludes this example regarding linear momentum and applications in fluid mechanics.